So everybody sees the slides, correct? Okay, so as we just said, so the paper is about auctions in which one of the bidders is a team. And this deviates from what is typical in auction theory. Auction theory typically assumes that the bidders are individuals. They can be individuals of many kinds, persons or firms, organizations. But at the end of the day, the basic unit, the participant in the auction, is just one thing. And what I do here, I consider an alternative where one of the bidders in my model is a group, is a collective consisting of several individuals. There are many examples for this, both in the real world and also in, for example, a clear example in the big world is spectrum auctions. There, the participants are typically telecommunication companies, which are big multi-agent entities. And you can think of also much simpler settings like textbook example of a couple of roommates who want to jointly bid on whatever, let's say a television set. From the standpoint of the auction, they are just one bidder, but from their standpoint, there are two guys with different preferences, different information, and so on and so forth. So these type of examples and stories are the motivation for this work. And to fix ideas, you can think of a couple of roommates who want to jointly bid on a television set as like the plain example to fix in mind. Now, this example, and more generally, these type of examples, they have two key economic features that I'm going to focus on. The first feature is that the good, which is being auctioned, is a public good. Yes, if you think about the two guys who are jointly bidding on a television set, if they win the auction, both of them can watch television. If they lose, then nobody can watch television. So first of all, this is a public good. And secondly, in terms of the economic problem that they need to solve, in terms of the challenge that they need to face, in addition to the usual strategic considerations that you find in any auction environment, here there is a preliminary issue, which is the issue of aggregation. They have private information and they need to aggregate it in an incentive compatible way in order to come up with an agreed upon course of action, what to do, how to play in the auction, etc. Okay, now in terms of the literature, there are several strands of the literature that are related indirectly to what I do, but not really directly. For the sake of being short of time, I'm not going to discuss it. If you wish later on to ask me about this or that reference in the literature, we can do it later. But now I think it's more efficient that I will go to my model and the results. Okay, so the framework that I'm going to talk about is the following. I consider an auction with two bidders. One bidder is a team. It consists of n symmetric individuals. Each one of them have a valuation for winning, which only he knows. Valuations are private and they are independent. These valuations are normalized to 0, 1, and each team member knows his own valuation, but doesn't know those of the others. He only knows the distribution from which they were picked. So this is the team. And this team, bidder A, competes against another bidder, and the other bidder, bidder B, is just one guy, a single ordinary guy. That's why I call him the regular bidder, player n+1, and he takes his valuation independently from some other distribution G. G may or may not be equal to F, it doesn't matter, and his type or his valuation is distributed either on the entire line or on some compact interval, it doesn't matter. So from the standpoint of bidder B, namely the regular bidder, the auction is an ordinary auction. If he wins, then he wins. If he loses, then he loses. And the fact that the bidder against which he competes is this complex n-person team, it doesn't really matter to him. from his standpoint, the situation is pretty standard. The novel aspect here is how things look like from the standpoint of the team. So let's talk about that. Suppose that the n valuations of the n team members are theta 1, theta 2, etc., up until theta n. In this case, if the team wins, the utility of player I or team member I is simply his valuation minus PI, where PI is the payment that he contributes in order to cover the payment that needs to be handed over to the auctioneer. Okay, so the sum of the PIs is the cost, namely the cost of winning, what you need to pay to the auctioneer when you win the auction. Now, as you can see, the n team members, they need to come up with two decisions. First of all, what to bid, how much to place in the auction. There's going to be just one single bid to be submitted on behalf of all of them, and they need to decide what this bid is. And secondly, they need to decide on the PIs. Namely, they need to decide how to distribute the burden of payment to the auctioneer in the event that they win the auction. How do they do it? I assume that they do it via the following simultaneous move game. They meet and they simultaneously announce reports. Each person, each of the n team members reports a number. Mr. 1 reports B1, Mr. 2 reports B2, etc., etc. All are non-negative. And as a function of the profile of these reports, two decisions are come into place. First of all, a bid aggregation rule maps this profile of reports into a single bid that will be submitted in the auction on behalf of the team. And secondly, a cost aggregation, a cost sharing rule determines how they're going to split the cost in the event that they win the auction. Now, as you can see, this framework has several moving parts: the auction format, type distributions, and of course, importantly, the mechanism. What is the bid aggregation rule? What is the cost sharing rule? So there are many things here, many parts of this picture that you can play with. And what I'm going to do now, I'm going to make different assumptions on these various components in order to look at different versions of this framework, different models. Before I do that, any questions so far?
Yes. So may I just want to ask, so you're taking a case where you have a team that they choose somehow a representative, and this person bids for the whole team. It's not that individuals which are part of the team, they participate as separate entities in the auction, and they can make individual bids, right?
There is,
So
you
you
can
have
think about
one team bidding as one player. This is
one player, yes, one player.
But I mean, okay, this is. I mean, it could be also the other way around or not. So I mean, they can collude. Of course, it's a different model, but they can collude in the outset and coordinate on the bidding. I guess you must have thought about this too, right?
So there is a big literature on collusion, and the literature on collusion deals with typically with something else. You know, we collude, we all go to the auction, but we let you win, and the rest of us, we place very low bids, so you will obtain the object for a cheap price. This is the typical collusion story. Now this makes sense when the item cannot be consumed simultaneously by everybody. We let you win and you have to compensate us maybe via transfers or something like that. All these things do not exist here, because when we win the auction, everybody wins it. There's no bidding ring in the traditional sense of this word. All right, so I will now continue, okay? All right, so the first version of this model is where the auction format is second price. When the auction format is second price, I can ignore the regular bidder, namely the outsider, the guy outside of the team, I can simply assume that he reports his type truthfully, namely plays his weakly dominant strategy, and therefore the game is in fact only a game between the team members. It's an n-person Bayesian game. Or to be specific, once you fix a mechanism, once you fix a bid aggregation rule and a cost sharing rule, you have yourself an n-person Bayesian game. Now let's see, what is the expected utility of a team member in this game when they report the vector of reports B1, B2, etc. Well, when they send the reports B1, B2, etc., the bid that's going to be submitted on behalf of all of them collectively is just A of these reports. The probability that they will win is G of this number. G is the distribution of outside competition. So I take this probability of winning and I multiply it by the utility conditional on winning. What is the utility conditional on winning? It's your valuation for the item times how much you have to pay. So this expectation here is the price that needs to be handed over to the auctioneer once the team wins the auction, and I multiply it by SI, namely by the share for which player I is responsible. So this is the expected payment of player I in the second price game. And here is a simple result which follows from general existence result for Bayesian games. If these functions are continuous, then the game has an equilibrium. To be precise, it has a monotone pure strategy equilibrium. This follows from general results for Bayesian games. For example, there's an econometrica paper of Phil Rennie that delivers this. Of course, his result is more general, but it can clearly be applied here. So that's about the first general thing I can say about the second price game. The second thing that I can say about the second price game, that you can never achieve efficiency. Why is that? Or to be more precise, the statement is as follows: fix whatever mechanism that you want. By the way, I did not tell you in detail the properties of the mechanism. A mechanism, as I said, is a bid aggregation rule that maps the reports into a bid, and a cost sharing rule that maps the reports into a point in the simplex. These are functions which are, I assume, they are well, you don't need to assume that they're differentiable, they're continuous, so they're differentiable almost everywhere, they're monotone in the obvious sense. These are well-behaved functions, but otherwise they're quite general. So fix any mechanism that you want, you have a game. This game may have, I don't know, 20,000 equilibria. Pick whatever equilibrium you want. The probability that the object will be allocated efficiently in this equilibrium, this probability is necessarily smaller than 1. Now, why is that? Well, it's not surprising because the item that we're talking about, from the standpoint of the team members, it is a public good. And therefore, inevitably, you're going to have some free riding in this model. What is the meaning of free riding in this model? It means that people will pretend to be of lower types than they actually are. And they will send low reports to the mechanism in the hope that the object will be 1, but they will not be asked to contribute and pay for it. That's the meaning of free riding, and therefore you cannot have here something which is analogous to truthful reporting, which is necessary for efficient allocation. Okay, so to summarize, these are the results for the second price version of this model. Equilibrium necessarily exists under general conditions, but no equilibrium can be efficient no matter what is the mechanism you're working with. Okay. Now I will move on to first price and all pay auction. So just a piece of notation. Given a mechanism AS, I will denote by this symbol and this symbol the corresponding game when the auction format is first price or all pay auction. And one more definition. I say that an equilibrium is an equilibrium with complete free riding if out of the n-person team, n minus one of them abstain, or alternatively, they report zero to the mechanism. They pretend to be the minimal type, and just one person, excuse me, I keep on receiving 1 million text messages from the kindergarten. I apologize. Okay, so in an equilibrium with complete free riding, what we have here is that there's only one representative who actually participates in the mechanism out of the entire team. He competes against the outsider, and all the other team members, the n-1 team leaders, they sit still and they don't say anything. So in fact, we have only two people who are competing against one another. One representative from the team and the outsider, and this is a two-person auction, which we can solve easily, no matter what the format is, we have a solution for that. So the only thing that needs to be verified in order to make sure that this scenario can be sustained as an equilibrium is to make sure that all the designated abstainers, all the people who are supposed to, the n-1 team members who are supposed to sit quietly and not intervene, we have to make sure that they have the incentive to do that. That even if their valuations are high, it will not be profitable for them to jump in and send some report to the mechanism in order to increase the team's bid. Okay. Now, why did I show you this definition of this extremely asymmetric equilibrium? It turns out that if the auction format is either first price or all pay auction, then this is the only possible equilibrium. So here are the results. If the first price game has an equilibrium, maybe it doesn't, but if it has, then it is necessarily an equilibrium of this kind, namely equilibrium with complete free riding. And the same result exactly holds for the all pay game. If under the all pay format there is an equilibrium, then the equilibrium is an equilibrium with complete free riding. Now, why is that? Let's have a look at a sketch of the proof, and the proof applies to either one of these theorems, to either one of these auction formats. So let's suppose that you have an equilibrium, which is not an equilibrium with complete free riding, namely an equilibrium in which at least two team members actively participate in the mechanism and they send some reports that have some impact, positive impact on the bid of the team. Once you have at least two guys who actively participate in the game, who actively participate in the mechanism, you inevitably have some free riding between them because of the nature of this environment, because we're talking about auctioning the public good. Now, what does it mean that there is free riding? It means that for each participant I, the report that he sends to the mechanism is zero if its valuation is sufficiently small. Okay, so a player may submit a player who actively participates in the mechanism. It means that his reporting function, the function that prescribes his report to the mechanism, is not identically zero. It takes some positive value, but nevertheless, it will be zero on some segment, on some interval of low types. This is necessarily true because it's a consequence of the free riding within the team. Now, once this is the case, that each and every member who does participate, nevertheless participate with the probability which is smaller than 1, then there is a positive probability that the team as a whole will send a zero bid into the auction. Okay, there's a positive probability event that everybody will be their respective cutoff, and the bid that will be eventually submitted on behalf of the team will be zero. And if that's the case, if there's a strictly positive probability that the team will hand over a zero bid, then what's the best response going to be for the outsider? The outsider who competes against the team, his best response will be to put 0, 2 if his type is sufficiently small. So it follows that if there is an equilibrium, which is not an equilibrium with complete free riding, then for every player, there is some cutoff such that underneath the cutoff it effectively reports or bids 0. And this cannot be an equilibrium because then everybody in these small segments of types will have an incentive to deviate to an epsilon bid or epsilon report. So this is, I'm not sure how clear it is to say it like this sketch without the math and without 100% precision, but this is the reason why you don't have an equilibrium other than an equilibrium with complete free riding. Okay, so this is what I have to say at the general level. So for any mechanism, for general class of mechanisms in the second price game, you always have an equilibrium. It is necessarily inefficient. In the first price or all pay version of the game, you may not have an equilibrium at all, but if you do have an equilibrium, then it is of this extremely asymmetric type, namely an equilibrium with complete free riding. Okay. And now the next thing I want to talk about is a version of the model in which you have a nice equilibrium. And for this, I have to go back to the second price format. And to show you an appealing equilibrium, I'm going to impose some assumption and I'm going to study a particular type of mechanism. Okay, so the auction format is second price. And the mechanism I'm going to look at now is the following specific one. First of all, I assume that bid aggregation is linear. The bid that is going to submit it on behalf of the team is simply the sum of the individual reports. And secondly, cost sharing is going to be done in a proportional way, like in a talloc function. Once we win the auction, each and every member I responsible for a fraction of the payment in proportion to his own report. Now, by the way, these two functional forms, I can generalize them if instead you can assume that the bid aggregation rule has this separable form for some function psi, and therefore SI has this form. It's the same. Without loss of generality, you can take psi to be the identity. Okay, so that's the model, and I need one more assumption, which is it's significant assumption, but it bites me a lot. I assume that the outside competition is uniform. It's uniform over a sufficiently large support. Uniform over some segment between 0 and n. And the result for this version of the model is the following. Suppose that M, that determines the size of outside competition, suppose that it is at least as large as 2 times n. Namely, it is at least as large as twice the size of the team. In this case, this model has a unique equilibrium, period. Turns out that this unique equilibrium is symmetric. All team members follow the same reporting function, which is given by this, where this number A is the solution to some equation, which is here. Okay, so how does this equilibrium looks like? There is this number A, which is, as I said, the unique solution to this equation. And given this number A, each team member computes an adjusted valuation. The adjusted valuation is just the maximum between 0 and his true valuation minus this constant. And then with this adjusted valuation, he sends a report which is as if he is the sole participant in an ordinary second price auction, and he simply reports his valuation. Now let's talk a little bit about the properties of this equilibrium. Okay, so this is the bid function. Now, if you take this model as is, the formula, as they are, etc., and you plug in n is equal to 1, namely you impose the restriction that the team is in fact a singleton, a single guy, then you obtain that this number A is 0. And you get that the bidding function is just the 45-degree line, namely the ordinary bid function of the weak dominance equilibrium of the regular second price auction. So in this sense, this model and this equilibrium offers a generalization of the standard IPV second price auction. Another thing which is related to the ordinary auction, which is generalized, another aspect of the second price auction, is the expected payment. If I compute the expected utility of a team member whose type is theta, I get this formula. And again, if you plug in n is equal to 1, you get a is equal to 0, and you obtain the standard payoff from the ordinary second price auction with uniform competition. So note that everything is summarized, that the single thing, the single number that differentiates this equilibrium, this model from the standard one, everything is summarizing this number A. And this number A, this is the only channel in the model through which the size of the team, namely N, and the type distribution, namely F, come into effect. Otherwise, the type distribution and the size of the team, you see that they don't appear here. They only come to expression via this single number, this key thing A. Now this A is in fact a cutoff. Yes, up until A, as you can see, if your type is A or below, you report 0, or alternatively you abstain, or alternatively you mimic the 0 type, call it whatever you want, and you report a positive report with a slope which is equal to 1, only if you're above this cutoff A. So in particular, it means that this number or this cutoff A, you can think about it as a measure or as a proxy for the size of the group of abstaining types. It measures how severe the free riding is. Now, since this is a measure or a proxy for how severe the free riding is, we would expect it to be bigger and bigger as n gets large. We would expect to have more free riding as the size of the team increases. And that's indeed the case. So let me say a few more properties about this A. So here A of n is this number A as a function of the size of the team, n. So first of all, indeed, this number is a strictly increasing function of n. Moreover, this function is increasing without a bound. The limit of A is 1 as n goes to infinity. And for a given fixed n, this cutoff an is to the right of some lower bound, which is an increasing function of the expected type. Now, so the meaning of this of property 3 here is that the bigger the expected type, the more and more A has to be to the right, and therefore the more severe free riding is. And why is that? What's the economic rationale? The rationale is that if each and every team member expects the types of his fellows to be high, then he has stronger and stronger incentives to stay out, because he believes that they are likely to send high reports, and therefore there's positive probability that the auction will be won, but he will not be asked to contribute. So in this way, we see the relation between the expected type and the corresponding free riding. By the same logic, you would think that free riding, alternatively, the value of this cutoff would go up if you take the model as is and you simply replace the type distribution by another distribution that first order stochastically dominates it. And that's indeed the case. That's the content of the following proposition. When everything else is fixed and you just change the type distribution, when you move from a certain distribution to a higher one, a one that first order stochastically dominates the original one, the cutoff can only increase. Namely, free riding can only get worse and worse. Oh, how do we do on time? Let's see. Oh, we're fine. Still
Yes,
have a
yes,
lot.
we are fine, Shiran.
We are fine. Yeah. I'm going pretty fast through the slides, so. Okay, and one more, wow, I'm going very fast through the slides. And one more thing regarding this model, this linear proportional model, is that the team's equilibrium expected bid increases with n. Now, there's just some algebra here, just some calculation. It's not necessarily the most interesting result in the world, but it's something to look at because there's this thing in public good models, which is called the group size paradox. That the bigger the group becomes, it does worse and worse. Now, here, what we see, if we think about the auctioneer and we think about the standpoint of the auctioneer, would he like to face small groups or bigger groups? You can think, well, maybe it's better to face a small group because with a larger group, you're hardly going to generate any money because of the within team free riding. It's not the case. When you have a larger team and a larger team, the free riding gets worse and worse, but nevertheless, in expectation, the bid that the team sends goes up. All right, and lastly, two more words about first price and all pay auctions. So if I take the model that I discussed in the last few slides, namely the one with these assumptions, linear bid aggregation, proportional cost sharing, and uniform outside competition, let's take this thing as is, but just replace the auction format from second price to either first price or all pay. Now, as you remember from a few slides ago, when I talked about the general results for all pay and first price, the general results are that if there is an equilibrium under either one of these formats, then it is necessarily this extremely asymmetric equilibrium, namely an equilibrium with complete free riding. Let's see how it manifests itself in the context of this linear proportional mechanism. Well, in the linear proportional mechanism, if the auction format is an all-pay auction, then the model has an equilibrium, and it is as we know, it must be an equilibrium with complete free riding, and indeed it is an equilibrium with complete free riding. However, under the first price format, there doesn't exist any equilibrium at all. You don't have an equilibrium with complete free riding, and therefore you don't have any equilibrium. Now, why is that? What's the logic here? The logic here is that, well, in order to sustain the situation in which just one guy in the team actively participates and everybody else sits still, you got to provide them the incentives to do that. That, you know, if I'm supposed to sit still and not to say anything and not to do anything, I should have the incentive to do that, even if my evaluation from winning is very high. Now, turns out that you can provide these incentives with the harsh, so to speak, payment rule of the all-pay format. In the all-pay format, once I increase my bid, once I send some positive report, it has a strong effect on how much I'm going to pay. And therefore, the situation where n-1 team members keep quiet, you can sustain it in equilibrium. The effect of your own report on your own payment is, informally speaking, softer under the first price rule. And in this case, indeed, at least for the case of uniform type distributions, you cannot provide these incentives, and therefore you cannot sustain this situation as an equilibrium. So that's the reason for the difference between these two results. All right, and now the last slide. So a few words about future research. So two topics or two avenues of follow-up research on this are the following. First of all, I plan to study a similar story, but without assuming a mechanism of the form that I have assumed today, namely a bid aggregation rule and a cost-sharing rule, which is some exogenous thing which is given to the team, and given this mechanism that just plays some simultaneous move game. Instead, I want to consider negotiation within the team. And negotiation within the team, it's qualitatively, it's a different story, because once you have negotiation within the team, the game that you get is a signaling game. Okay, for example, one person makes an offer to another team member. How about we're going to submit such and such bid, and then we split the cost. So this communication, this interaction within the team is in itself a signaling game, and it's something which doesn't exist in the model that I show you today. So it's maybe something nice to look at. And another thing is that in the model that I showed you today, only one of the bidders was a team. And on the one hand, it allows me to focus entirely on the within team complications, namely the information aggregation, free riding, etc., etc. A different thing would be to consider a model with several teams. I've started to work a little bit on that, but I don't have enough result to present something solid. But one thing that I think is going to be the case, that whether you consider a single team or competition between multiple teams, the results can be very different. So that's it.
Okay, thank you, Shiran. Do we have any questions from the audience? Shiran, I would like to ask then one question. On slide, I think 26, I think when you started talking about the linear proportional model.
Yes, I'll go there.
I'm not an expert. Yes, I'm not an expert on the field, so maybe my question is really silly. I understand the bid aggregation to be linear, as you said. How can it be non-linear, but not theoretically, in practice? How can this the psi function be not the identity in practice?
What do you mean in practice? I can say, listen, you report a number, I report a number, we take the square root of this, and the square root of your x plus the square root of my y, that's the bid that we're going to submit. Why it's not a problem, right?
Because, as I said, my question might sound silly, but in practice, would we ever see this type of bidding?
In terms of practice, I think that this form is maybe the most natural there is, but you know, in this I completely agree with you. But you know, once you write a theory model, then you write this form, you're always in the danger of, hey, why this specific form? Then here is a footnote. In fact, you can assume if you wish something more general, it doesn't matter. Okay. As long as you have the separability between the individual reports and the proportionality in this way, it's as if you have the identity.
Okay. Do we have any other question?
One question, or maybe two.
Okay.
Yes, okay, so I'm not much in option theory, so maybe what I say is not very intelligent. So anyway, so the way you presented this is like bidding for a public good, right?
Yes.
In terms of the team, but with your example with a television set, it's not exactly, I mean, you can see it as a public good, but suppose that I'm the highest bidder within the team, so my BI is very high, and okay, we split the cost according to your rule, but we somehow can also split the benefit. So I say, well, if I'm the higher bidder, I can also enjoy more hours than you watching television. So I don't know if this is a standard case in auction theory, or this is something that you could consider introducing a benefit function. So I bid more within the team, and I'm allowed to use the television set more than the other. So how this would change the results? And the other question is, could you explain why the size paradox regarding free riding does not work in your case? So you say as the team becomes larger, you the incentive to free ride does not go up. So if I understood well, this was your case. Can you explain what's the reasoning behind this?
Yeah, so two things. First of all, about your first remark, it's an excellent remark, and it's a, first of all, this is an alternative, and I think it looks very interesting model that, you know, once we have the reports and it determines what bid we're gonna place, how we're gonna share the cost, and how we're gonna use the item that we obtained. Then I can determine how much television we watch or whatever. In terms whether it's common or not in auction theory, I'm not sure myself. In one sense, the answer is probably not, because I don't think that there is a lot of work in auction theory on this. There isn't much work. Maybe there is some model in public economics with similar features. I don't know, but it's an interesting variant to look at. So I don't know. Yeah, I know it's interesting, but I'm not sure how it's gonna change. Yeah. About the second result, so the fact that the smaller than he actually is. So this is one effect. The other effect, that you have more and more individuals sending reports. So the second effect dominates the first effect. But why does it dominate the first effect? The math. I was disconnected for a minute, right? For a second. But so the why one effect dominates the other, I don't have an intuition why is that. It's just how it happens to be.
Thank you. Thank you.
Thank you very much.
Does anybody else want to ask something? No. Okay. Then, Shiran, thank you again for accepting this invitation. And like I said, if you could please email me the slides, so I will upload them to the same link I gave you. Τον χάσαμε.